In this unit, we are going to look at acid strength and comparing strong acids and weak acids. Our objective in this unit is to identify acids as strong or weak and to understand the difference in weak acids by comparing the Ka values. Earlier on in chemistry, you should have learned the difference between strong electrolytes and weak electrolytes. It tells us something about how much a molecule dissociates. For example, something like sodium chloride in water. Sodium chloride is a strong electrolyte. It dissociates completely into the sodium ions and the chloride ions. Well, talking about strong acids and weak acids is actually the same as talking about strong electrolytes and weak electrolytes. A strong acid is one that completely dissociates or ionizes in water. A weak acid is one that does not completely dissociate or ionize in water. We need to remember that just because something is a weak acid, it can't do a lot of damage. HF is a weak acid because it does not completely dissociate in water. However, HF can be very dangerous to handle if not done so correctly because of the small size of the molecule. It actually can dissolve glass, and when we have HF, we have to store it in a Teflon or plastic container. When we look at strong acids and weak acids, we can actually classify them very easily. Notice that when we list the strong acids, we say the strong acids. There are actually 6 of them: hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric. Notice that sulfuric has 2 H's or 2 protons. We're only referring to that first dissociation. It will completely dissociate. The second one will not. When we look at the list of weak acids, we note here that we're saying some weak acids. These 6 strong acids are all of the strong acids. If it's not one of these 6, then we know it must be a weak acid. We're not going to be able to list all of the weak acids because there are far too many of them to list all of them. So the best thing to do is memorize or learn all of the strong acids and know that if it's not one of those 6, it must be a weak acid. Just as we've looked at the law of mass action for equilibrium reactions, we looked at the value of Kw for the ionization or dissociation of water, we can do the same thing for acids. In this case, we are looking at a weak acid, and we know this because it has an equilibrium arrow. If we have a strong acid, we would get the complete dissociation, so something like HCl going to H plus Cl minus, and we would not be writing an equilibrium expression or a law of mass action for HCl. When we look at our weak acids, we have our H plus as a product, remembering that that's the same thing as H3O plus, and we have A minus as a product, so H plus times A minus, over our HA concentration, which is our reactant. It is an aqueous substance, so we will include that in our law of mass action. So we're using the same expression that we've used throughout these units. For K, we just put A as a subscript to represent that we're talking about the equilibrium constant or the dissociation constant associated with an acid. We have tabulated values of acid ionization constants, these Ka values, also known as acid dissociation constants. And we can use these reference values to determine the relative strengths of acids. HCl has a very large Ka value, much greater than 1, because we have almost exclusively products and none of our original HCl as a reactant. So the number in the denominator is going to 0. When we look at our weak acids, the ones we've selected here, we have chlorous acid, nitrous, hydrofluoric acid, hypochlorous acid, and hydrocyanic acid. And we've written these in order from the strongest to the weakest acid strength. So even though chlorous is a weak acid, of this particular set, it is the strongest of these weak acids. We see that our Ka value gets smaller and smaller and smaller, indicating that less and less of the acid is dissociating or ionizing, until we get down to our hydrocyanic, where this is the weakest of this set of acids. Because what we're looking at is our acid dissociating into H plus and A minus. This is at equilibrium. So when we get down to very small Ka values, it tells us we have very little of our product forming, very few of the H plus and A minus ions forming, and that lets us know this is in fact a weak acid because we're looking at a very small amount of H plus relative to the amount of HA we have present. Another way to talk about acid strength is actually to look at something called the pKa values. In the same way that pH equals the negative log of H plus concentration, I can also find pKa, which is simply the negative log of the Ka value. If we put the prefix p in front of anything, all it means is take the negative log of that number. I could take the p of my shoe size, and to find that, I would take the negative log of my shoe size. Now this doesn't have a lot of value because it doesn't really matter what the p of my shoe size is, but it's just to let you know and to remind you that whenever I see p, I always take the negative log of that number. So I can go from pKa equals negative log of Ka. If I know Ka, I can find the pKa, or I can do the reverse. I can find the Ka by knowing the pKa. In the same way that we went from H plus concentration to pH and vice versa, I can take 10 to the minus pKa equals the Ka value. In the next module, we're going to look at how we find the pH of an acid solution for both strong and weak acids.